So here's a second example for the work energy theorem. We have in this problem, an object is pulled along a ramp, but the object starts and ends at rest and thus has no overall change in its kinetic energy, which is important. The figure shows the situation. A rope pulls a 200 kilogram sleigh, which you may know, so our mass is 200 kilograms, up a slope at an inclined angle of 30 degrees through a distance d of 20 meters. So our angle is 30 degrees, distance d is 20 meters. The sleigh and its contents have a total mass of 200 kilograms. The snowy slope is so slippery that we take it to be frictionless. How much work is done by each force acting on the sleigh? So if I draw a picture of what's happening here, we have our incline, and then we have our sleigh that is on the incline. Now, if I draw my free body diagram, I have the tension force upwards, the normal force perpendicular to the surface of that incline, and then, of course, we have the force of gravity straight down towards the center of the earth like this. Now, we're going to actually break that force of gravity vector down into x and y components like we always do. So if we do that, we get the force of gravity in the x direction, and then the force of gravity in the y direction. Now we can see that this sleigh right here is going up this incline in that direction. So that is our displacement d. So if you recall, any forces that are acting perpendicular to the displacement are doing no work. So that means that the normal force and the force of gravity in the y direction do no work. And that's because the cosine of 90 degrees, and that's the angle between those forces and the displacement, is equal to 0. So therefore, those two do no work on that object. Now we need to find how much work the force of gravity in the x direction and the tension force do on this sleigh. Now we don't know what exactly the tension force is, so let's do the force of gravity in the x direction first. Now remember, in order to solve for the force of gravity in the x direction, we use the force of gravity times the sine of the angle of incline, and they give us that this angle is 30 degrees. I'm sorry if you can hear Rowdy barking. And that's because of like triangles. So we end up getting mg times the sine of the angle, which we know the mass is 200 kilograms, times the acceleration of gravity, 9.8, times the sine of 30 degrees. So our force of gravity in the x direction ends up being, here's my calculator, 200 times 9.8 times the sine of 30. We end up getting 980 newtons for the force of gravity in the x direction. And then in order to find the work done by that force of gravity in the x direction, and really this is the work done by the force of gravity, we know the y direction force of gravity doesn't do any work, but that doesn't mean that the force of gravity doesn't do any work, okay? So we end up getting, I'm sorry, you can see Rowdy in the background like going in and out. He's a little pest. So we get work done by the force of gravity is equal to the force of gravity in the x direction times the displacement times the cosine of theta. Now remember, this theta right here in this problem, in this equation, is going to be the angle between the force and the displacement vector. So in this case, we're looking at this force vector, and this force vector is down the incline. Now the displacement is up the incline. So the angle between those two is going to be 180 degrees. So here, when we're plugging in numbers, we get the work done by the force of gravity is equal to 980 newtons times the displacement, which is 20 meters, not newtons, times the cosine of 180. Now the cosine of 180 is just -1, which makes sense because the force of gravity is acting opposite the displacement. So that's going to be a negative work done by that force. So we get 980 times 20 times -1. And we get work done by the force of gravity is equal to a negative 19,600 joules. Right, so we know the work done by the force of gravity now. And then now what we can use here is the work kinetic energy theorem. And the reason we can use this is because we can see that because we know that the net work done on the object will equal the change in kinetic energy, and we know that the change in kinetic energy is 0. So what we do here is we add up all the work done by all those forces. So the work done by the force of gravity plus the work done by the normal force plus the work done by the tension force, because those are the 3 forces acting on this object. Those all equal the change in kinetic energy. Now again, remember, the change in kinetic energy is 0. We also know the work done by the normal force is 0, and we just found the work done by the gravitational force. So we get a negative 19,600 joules plus 0 plus the work done by the tension force is equal to 0, which ends up being the work done by the tension force equals a positive 19,600 joules. All right, so that's how you find the work done by the tension force. Now, of course, we know that work is going to change the total energy. So in this case, we're not changing kinetic energy, but we are changing potential energy because the work done by those 2 forces are lifting that sleigh up there. So we can actually find how much our potential energy increases by using this triangle right here. We know this is 20 meters. This angle right here is 30 degrees. So if we find our height, we know that the sine of 30 will be equal to h over 20. So that means the height is equal to 20 times the sine of 30, which of course is 10. And then we know potential energy, or U, is equal to mgh. So we get mass 200 kilograms times g 9.8 meters per second squared times the height 10 meters. And so we get 200 times 9.8 times 10. And that, what do you know, is 19,000, I keep saying 1,000, 19,600 joules. Right? And that is not a coincidence, right? This work being done by that tension force is increasing that potential energy by the same